Hello everyone, welcome to this presentation. This time we are going to see an introduction to the Raspberry Pi Pico microcontroller board. So in this video we will see first an introduction, then we will show the Pico schematics and some details related to the configuration of this board. We will see how to install the Python IDE that we are going to use, which is Thony. And finally, we will show some examples of implementation of different programs on the Raspberry Pi Pico. Here are the main features of the Raspberry Pi Pico microcontroller board. It is based on an RP2040 microcontroller. It incorporates 2 MB of flash memory for the user programs and data. It operates at 125 MHz by default. It can be supplied from the micro USB connector at 5 volts. As we will see later, internally it operates at 3.3 volts. It provides a total of 26 multifunction 3.3 volts general purpose input outputs GPIO, and 3 of these GPIOs are ADC capable, so they can be used for analog to digital conversions. The core of the Raspberry Pi Pico is the Raspberry Pi 2040 microcontroller. Here are some features of this microcontroller. It is based on a dual-core Cortex M0 Plus that can operate up to 133 MHz. It has an on-chip PLL that can achieve variable core frequency, 16 KB of ROM memory for startup, boot, etc., up to 16 MB of external flash memory driven via SPI, 264 KB of static RAM. It provides also an onboard USB 1.1 that can operate as a device or as host, a total of 30 multifunction general purpose input outputs. 4 of them can be used for ADC conversion. It can operate in a range of voltage from 1.8 to 3.3 volts. The Raspberry Pi Pico voltage is fixed at 3.3 volts. It also incorporates a 12-bit 500 kilosamples per second analog to digital converter, 2 UARTs, 2 I2Cs, 2 SPI, and 16 PWM channels, 1 timer with 4 alarms and 1 real-time counter, 2 programmable input-output blocks that can implement up to 8 state machines in total, and finally it can emulate interfaces such as SD card and VGA. Here is a photograph of the Raspberry Pi Pico. We can see in the middle the microcontroller unit RP2040. Here is the oscillator, is a 12 MHz crystal oscillator, but then this signal internally is increased up to 125 MHz using the internal PLL plus VCO structure. Then here we have the chip corresponding to the external 2 MB flash memory, which is driven via SPI by the microcontroller unit. Here in this part we have the power supply to convert the 5 volts coming through the micro USB into 3.3 volts to supply the microcontroller unit. As we are going to see, this is a current mode buck boost converter. Then we have the pins corresponding to the GPIOs surrounding the board. We have a push button here to do some actions, and also we have an LED here, and finally we have the connector for the micro USB, so it can be used to supply the board and also to connect the board with the personal computer. So let's see now some details regarding the implementation of the Raspberry Pi Pico. Here is the schematic corresponding to the power supply. We have the input coming from the micro USB, so we have this voltage here, V bus, a series diode, and then this voltage here VCs. Here we have the power converter, which is a synchronous buck boost converter with average current mode control. It can also be controlled by this signal PS in order to select the operating mode. This can be done using this output of the microcontroller unit, the GPIO23. So if the user selects here this output to be 0, then the converter will operate in pulse frequency modulation mode, which is good for the efficiency, but not so good for the output voltage ripple. If we select PS equal to 1, then the converter will operate at fixed frequency, which is good for the ripple, but the efficiency is going to be lower, especially at light loads. We can also activate and deactivate the chip by using this enable input. As default, this input is activated, so the chip is going to be operating. But this line here is connected to pin 37 of the board, so externally we can decide if we want to turn off the converter at any time. Finally, we have this signal here, which is connected to the GPIO24 of the microcontroller. And this is intended to have the possibility of reading the status of the VBus voltage. So if we have here 0 level, then it means that there is no power supply connected to VBus. And if we have a high voltage here, then this means that we have connected VBus. So the microcontroller can recognize if there is any power supply connected to the micro USB connector. With this arrangement for the power supply, there are several possibilities to supply the microcontroller board. We are going to see some of them. For example, if the micro USB is the only input to supply the board, then we can tie together VBus and VCs by doing this connection between pin 40 and pin 39, so we can bypass diode D1 and save energy, so the efficiency is going to be higher. Other possibilities to supply the board externally, in this case we can use a voltage source applied to the pin VCs, and then the voltage source can be in between 1.8 and 5.5 volts. So this is very convenient because we can use two AAA batteries to supply the board. This is why they use here a buck boost converter, so they can generate 3.3 volts at the output even when the input is below 3.3 volts. If we do an arrangement like this one, then we cannot connect the USB here, the power supply, through the USB, because then we will have a short circuit. So if we want to keep the operation of the micro USB, then what we can do is to remove diode D1, which is not very difficult because the package of this diode is quite big, so it can be removed easily. Otherwise, what we can do to keep the possibility of supplying the board from an external power supply or from the micro USB is to add this diode here, this Schottky diode, in series with the external voltage source. So in this case, the board will be supplied from the power source which has the maximum voltage. But of course, in this case, we are going to have some extra losses in this series diode here, and also we have some voltage drop, so the range of the external voltage source is lower. Here is other interesting circuitry of the board. In this part we have a circuit to measure and monitor the power supply voltage VCs. Particularly here we have the voltage VCs divided by 3. So through this input here, GPIO29 connected to the ADC converter channel 3, the user can monitor the status of the battery that is being used for supplying the microcontroller board. Here we have the circuitry corresponding to the onboard LED, so it is controlled by the pin corresponding to GPIO 25. In this part here we have the circuitry of the flash memory chip of 2 MB in total, and here the user is going to have the programs. Here we have the push button that is controlling the boot up process. So if we connect the board to the micro USB while pushing this button, then the flash memory boot is going to be disabled and it forces a USB boot, so our board is going to operate as a USB drive. If the button is released when supplying the board, then the boot is going to be done from the flash memory. So it will start running the programs stored in the flash memory. Here in this part we can see the 12 MHz crystal oscillator. As we have seen before, this frequency is multiplied internally in the microcontroller to obtain the 125 MHz operating frequency. And finally here we have the connector with all the pins surrounding the board. So as we can see, most of them are GPIOs. We can highlight this pin number 30, which corresponds to signal run. This is the reset pin. So if we are interested in having the possibility of doing an external reset, then we only have to connect a push button here from pin run to ground. Here we can see the rest of the circuitry of the board corresponding to the microcontroller itself, the RP2040. We can highlight here the circuitry corresponding to the AC voltage reference. As we can see, the voltage reference is generated from the output of the switch mode power supply, here generating this 3.3 volts. So we can make two remarks here. The voltage is going to have relatively high noise due to the switching noise. And the other point is that we are going to have an offset voltage of around 30 millivolts because we have some consumption here of current into the input of the ADC converter, which is approximately 150 microamperes. This current multiplied by 200 ohm here, which is the value of this resistance, gives 30 millivolts for the offset voltage. So if we want to improve the voltage reference as it is suggested in the board dataset, we can do like this. We can connect a precision voltage reference to this point, which is available on the connector, and with this we can generate here a very accurate 3-point voltage reference, and then this resistance here is used to supply a current of around 1.5 milliamperes into the precision voltage reference. With this we know the most important features of the board. Here we can see a drawing showing all the pins with their different functions as obtained from the manufacturer's information. For more information, I recommend you to visit these links here with the information corresponding to the Raspberry Pi Pico dataset and with the information corresponding to the Raspberry Pi 2040 microcontroller. Also, I would like to highlight the low cost of these devices. The board is around 3.5 euro and the microcontroller cost is around 0.90 euro. Let's see now how to program the board using MicroPython, which is a small version of Python for this kind of devices. We are going to use Thony, which is a very convenient IDE that we can download from this link here. Once the program is downloaded, we only have to configure the program to drive the Raspberry Pi Pico, and for this the easiest way is to go to this part here of the screen at the bottom and select Configure Interpreter. With this, we can select here the MicroPython for Raspberry Pi Pico, and it will install all the necessary firmware for the Raspberry Pi Pico microcontroller board. Once everything is ready, we only have to connect the Pico to the micro USB in our computer, and then we will see a screen like this showing that there is a Raspberry Pi Pico connected and ready for operation. This is the circuit that I have implemented in order to do some testing with the board. We can see that we have connected here an LED to GP0. We have a push button here connected to GP1. GP2 will be used to generate a PWM output. And here we have connected a potentiometer in order to generate an analog input into GP26. So here in this photograph we can see the different devices. This is the LED, the push button here, and the potentiometer on this part of the photograph. We are going to see now some examples. Just a couple of comments about the IDE. Here we have two parts in the screen. One is this part here in which we can write our programs, and the other part here corresponds to the shell. And this is very useful because here we can print messages, we can print results, variable values, and so on. So it is very interesting to monitor the operation of our board. Finally, when we have our program ready and want to operate the board in a standalone fashion without connection to the computer or anything, then we only have to save our program in the Raspberry Pi Pico with the name main.py. Let's see now some examples here. We have the board connected to the computer on the left, and here we have the Sony environment. So let's open our first example. We can select if we want to open the program from the computer or from the Raspberry Pi Pico itself. So in this case I have the program in my computer. I select example 1. So this is a very simple example. Here we are going to control the LED from the button. What we are going to do is when the button is on, we are going to turn on the LED. And when the button is released, then we are going to turn off the LED. As you can see here, we have a library called machine from which we import the function pin. And we define an LED handle with the function pin at pin number 0, GP0, and in a configuration as an output. The button is defined in this way. At pin GP1, it is configured as an input and with a pull-up resistance, because we are using just the push button connected from this pin to ground. And then we are continuously performing this action. If the button is pressed, then we are going to have a 0 at pin 1, and then we are going to activate the LED. And if the button is released, then we are going to have a high level at the input 1, and then the LED is going to be off. So we can run the program now by clicking here on run. So now we can see that the program is running here on the shell. So right now we can go to our board and press on the button. So we can see that each time I press on the button, the LED is going to be on. We can stop the program by clicking on stop. And let's see now another example, second example here, which in this case corresponds to a blinking LED. So we are importing two functions from machine now here, pin and timer. LED is defined as before, and then we define another handle for the timer here. So what we are doing here is defining a function which is the blink function depending on the timer, and the function what is going to do is to toggle the state of the LED. So now with this call here to the function timer init, we can select the frequency at which is going to be performed the blinking. Also, we select the periodic option for the timer, and the callback function that we are selecting here, which is blink, is the function that is going to be performed each period that we have selected for the timer. So let's run again the program here. We click on run, and then we can see how the LED is blinking at a frequency of 1 Hz. We can stop the program now and change the frequency here, for example, to 2 Hz, so we can see how the LED is going to blink quicker, and maybe increase to 5 Hz, so we can see the LED blinking very fast. Let's see with this example how to do the standalone operation. For this, we only have to take our program and save it as a main program into the Raspberry Pi Pico. So I select the Raspberry Pi Pico here. I select the main.py and say OK. I can say that I want to overwrite it, say yes. So right now it is ready for standalone operation. So I can unplug it from the computer. So now it is unplugged. Now I can close even the Sony environment and then just plug in again the USB only for supplying the board, and we can see how it is operating in standalone mode. Let's see a third example. Example number 3 here. In this case, what we are going to do is to measure the value of the analog DC level that we are injecting into the board in pin 26. So in this case, we are importing the function ADC and the function pin, and also the function time to do the measuring of the sample time. Here we are defining this handle ADC for the pin, analog pin, in this case 26. And then what we are going to do is continuously measuring the value of this analog signal every 0.5 seconds, and then we will print on the shell the value that we are reading from the pin. So let's run the script, and we can see here the value that we have. In this case, it's the maximum value. So we are having a voltage that is close to 3.3 volts. I'm going to act now on the potentiometer to change the DC value of the analog signal. So we will see how the output voltage is going to change accordingly to this value. So we can see how the value now is decreasing. So from this value, it is very easy to calculate the DC voltage that we are having at the input. So let's see now a final example. Example number 4. In this case corresponds to an example for generating a PWM signal. So we can see here we are importing the functions pin and the function PWM. We are defining here a handle PWM for pin 2, and then we only have to use these two functions here for selecting the duty cycle with integer variable of 16 bits. So here we are selecting a duty cycle of around 0.5, and with this other function we are setting the frequency of the output, in this case 100 kHz. Here in this slide we can see different outputs for different values. For example, here in the first example we are selecting the value that we have seen before, duty cycle of around 0.5 and 100,000 Hz for the output. So we can see here the PWM output, which is quite good. with very low turn on and turn off times. This is another example with different values. In this case here we are giving the value of 20,000 for the duty cycle and 500 kHz output. So here this is the resulting waveforms that I have obtained in the scope. This is the frequency measured is 500 kHz and the duty cycle is around 0.31. And finally, this last example here is for the same value of the duty cycle, 20,000, and for an output frequency of 1 MHz. So we can see that still, even at 1 MHz, the waveforms are pretty good. Here the duty cycle in this case is 0.6. For more information about the PWM module, I recommend you to take a look at the dataset of the microcontroller. As we have seen, when programming in Python, it's very important to get familiar with the different libraries and functions. So for more information, I recommend you to visit this link here. Let's take a quick look at this website. It is very easy to use. If we want, for example, to get information about the function timer.init that we have used right now, then we get this link here immediately, so we can go and get all the information regarding the operating mode, the period, callback function, and everything. Finally, a comment on how to program the flash memory directly. From our Python program, we can generate a UF2 file with the program and send it to the microcontroller unit, to the board. Also, this can be also done by programming in C language, and then it is possible to generate a program for the microcontroller. So once we have this UF2 program ready, what we have to do is to hold the push button, connect the USB port to the computer, and then we will see how a new drive appears in our computer. So we only have to drop the UF2 file on this unit, and then we will program the flash memory. So this is especially interesting when we want to program our Raspberry in C language in order to optimize the operation of the microcontroller. Well, this concludes my presentation today. I hope it's useful for you, for your future activities. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.